Welcome everybody to the last day of this workshop. And our first speaker today is Cecilia Gonzalez Tokman, and she will talk about Lyapunov Oseledets spectrum for transfer operator cocycles and perturbations.
Thank you. And I want to thank first the organizers for this really interesting and inspiring conference, and also for the opportunity to present this work, which is joint work with Joshua Peters, who is a student at the University of Queensland, and also Anthony Quas from the University of Victoria. So the talk will be divided in three parts. The first one is a relatively long introduction, where we're going to talk about random dynamical systems and also about the words which appear in the title, transfer operator cocycles, and also Lyapunov Oseledets spectrum. And then we're going to talk about two examples where we have been able to compute or approximate this spectrum, namely random Blaschke products and also random metastable maps. So random dynamical systems, we'll be talking about systems in discrete time. So we're composing maps T indexed by some omega. In most of the talk, D will be just the interval or the circle, and omega will represent the state of an external system that we call the driving system, or we also think of it as the state of the environment. And this system is evolving completely independently to the system that we are observing. So this is has its own dynamics given by sigma from omega to itself, and in the context. And so, you know, this could be the first map that we apply when the environment is omega, sigma squared omega, and so on. And the context that was studied by initially Kiefert, Arnold in the 80s, 90s, assumes some conditions on this driving, which is invertible, ergodic, and measure preserving transformation. So this is quite a general setting which generalizes the case of autonomous systems, where of course we just have one map and we repeat it over and over, which is the usual context for dynamical systems. But we can also have cases of noise driving the system, or also something like seasonal forces. For instance, we could have that sigma is a quasi-periodic rotation. So that will be the setting for this talk. We have an external system, sigma. We have different evolution rules dictating the dynamics of the system when it's in, say, the environment is omega. And as we have seen in various talks this week, starting from Monday, I think, with Roberto's talk, and all the way to last talk yesterday by Danielle, will be trying to understand the dynamics or the statistical properties of the system using transfer operators. And I won't give the formula, we have seen it several times. I'll just give this picture to illustrate that transfer operators tell us how dynamics evolves at the level of densities or the distributions of particles. And these are linear operators acting on some Banach space. And so the random dynamical system for us will be this top tuple encoding the driving system, the Banach space, and transfer operators, and the cocycle rule tells how to go forward in time. So we have to compose, of course, the different operators corresponding to the different maps. So again, mimicking what has been successful in the case of autonomous systems, we would like to have some sort of spectral tools to analyze the long-term dynamics in the system, and that's why we look into multiplicative ergodic theorems. So when they apply, what we get are precisely spectral type decompositions for non-autonomous systems, and these decompose the space of densities, if you want, into nonlinear time-varying modes, ordered by decay rate. So this is a comparison in the case of autonomous systems. If we have a quasi-compact operator, we have isolated eigenvalues and associated eigenspaces. in the case of random dynamical systems, we have a similar quasi-compactness property, and we have Lyapunov exponents instead of eigenvalues and Oseledets spaces instead of eigenspaces. And the main difference is that these Oseledets spaces are not constant, but they are evolving over time, or they depend on the environment, but they are equivariant. And the second difference is that we don't have a one-step expansion or contraction estimate, but rather an asymptotic rate of growth or decay given by the Lyapunov exponents. So that's the picture a little bit more precisely. What we get in the case of quasi-compact random dynamical systems when multiplicative ergodic theory applies is at most countably many Lyapunov exponents. 0 corresponds to the leading Lyapunov exponent, similarly to 1 being the leading eigenvalue of the Perron-Frobenius cocycle. And these are like the logarithm of the Weyl-Polycott resonances that, again, we heard in a few of the talks this week, including Daniele and Sakshi yesterday. And the Oseledets spaces give us splitting of this Banach space, and this is omega dependent, and the jth space will be associated with the jth Lyapunov exponents, and vectors there will decay at that rate, and there could be complement corresponding to the part that is inside the essential spectrum. But as in the autonomous case, everything in that complementary space decays faster. So it's not as important for the long-term dynamics. So we'll denote by sigma the Lyapunov spectrum. So in the context of this talk, the leading Lyapunov exponent will be 0. And we're going to use mu's instead of lambdas because lambdas could have multiplicity, but if there's multiplicity, we'll repeat these numbers in the mu's. And again, similarly to how the peripheral part of the spectrum tells us information about the long-term statistics of the dynamical system, we have that the leading part of the Oseledets or Lyapunov Oseledets decomposition tells us about the long-term dynamics of random dynamical systems. For instance, going back to Kiefer and Buzy, the first Oseledets space encodes long-term equilibria for the system. For instance, the statistical properties of observables are encoded in measures which are pretty much encoded by this first Oseledets space. If mu2 is less than 0, we have exponential decay of correlation. And well, there could be second and higher Oseledets spaces which are associated with slowly mixing modes or phenomena such as metastability. So that's the idea. And let me show you what I think is the simplest picture where we can see this. So two-state Markov chain. So we have a stochastic matrix, column stochastic in this case, representing the one-step transition. So in the autonomous case, well, it's just an eigen value problem, thanks to the Perron-Frobenius theorem, telling us that the long-term behavior of a system governed by this transition is just going to converge to the equilibrium given by this first eigen value. And what I'm illustrating in this picture is time on the horizontal line, and on the vertical line, I'm plotting two evolution corresponding to two different initial densities, one which is completely concentrated on the first state that we see that quickly decays. So we're plotting the first component of the vector, and so quickly decays to this value, 0.1667. And similarly, we start with all the mass on the second component, really quickly, again, we decay here. So that's the very simple picture in the autonomous case. What happens if we now change the dynamics? So now we are not having the same law every time or the same dynamics. For instance, if we have a periodic dynamics, what we see in the long term, of course, cannot be as simple as before. It will reflect the oscillations of the environment, but what remains similar is that independently of the initial distribution, we get after some quick time this synchronization. So these blue and red trajectories get together in this kind of purple modes. Very similar to what happens in the case of general non-autonomous systems. Of course, in the long term, we cannot expect something simple if what happens with the environment is complicated. But if multiplicative ergodic theory applies, what we get is this, for instance, this loss of memory, and what how we could think of these bars here is the first component of the first Oseledets space. So Oseledets splittings and also multiplicative ergodic theory has a long history. By now, it started with Oseledets in the 60s and Ragunatas in the 70s for matrices. Several people have worked on this. For instance, Weyl had a version for Hilbert spaces. He was interested in some turbulence phenomena. And then also Magnet, Thielen, Lian, Blumenthal developed generalizations to Banach spaces. This is not a complete list, but is the one that is closest to our work. And all these results have an Oseledets splitting in the case where the operators or matrices are invertible or injective. But transfer operators are often not invertible, for instance, for expanding maps or piecewise expanding maps. And this is why semi-invertible multiplicative ergodic theory was developed first by Froiland, Lloyd, and Quast for matrices and operators. And later I also joined this team. And we have by now what we think are quite satisfactory kind of abstract results giving this framework of multiplicative ergodic theory. So the questions now are, well, can we find some examples where we can compute some of these objects and what happens with stability? For instance, of course, stability is an interesting question from the mathematics point of view, but it's also relevant from applications. Some applications really motivated all of this work. And so it's important to know how model error or noise or numerical schemes affect these data. So by data, I mean the Lyapunov exponents and the Oseledets splittings. And I should mention a few results. So of course, in the autonomous case, there's quite a bit known. There's, for instance, the book by Kato, but in the context of quasi-compact operators, there's the result by Keller and Liverani in 1999 giving stability. In the case of random dynamical systems, there are some results by Ledrapie and Young in the 90s about IID perturbations of invertible matrix cocycles. Ox has a result relating stability of Lyapunov exponents and Oseledets spaces. And in the context of maps, Baladi, Konda, Schmidt has work about random perturbations of non-random systems, and Bogenschutz has a result about uniformly hyperbolic splittings. And I should say, since we have worked in this, there have been other results, for instance, by Kriemings, somewhat extending the results of Bogenschutz. But there's a difference with the case of autonomous systems in that we know there are some instability results. So in the case of autonomous systems, we usually expect stability, but it's kind of not really the case in the case of random dynamical systems. And there are these works of Bocchi and Viana showing that there's some instabilities, but stability is expected to be kind of the rule, much more general. And for instance, I think last week or the week before, there was a preprint by Avila, Eskin, and Viana about continuity of Lyapunov exponents for IID products of invertible matrices. So it's expected, so stability is expected to be more the rule. And we're mostly interested in transfer operators. The first stability result that we got some time ago was about the top Oseledets space, or the random invariant measure, under quite general perturbations. And then we studied some models, not exactly for transfer operators, and got some results about matrix cocycles and some operators in Hilbert spaces. But we really wanted to know more about what happens with, say, second and higher spaces. So let me now tell you what we got in this first case study, which is random Blaschke product cocycles. So these are random Blaschke products. These are functions which depend on a complex variable. There are several parameters here. So Z is just unit length vector, so just giving a rotation. The AJs are the zeros of these rational functions, and they are assumed to be inside the disk of radius 1. And so these Blaschke products are analytic on the disk. And there are some conditions one can check on the coefficients that ensure that these give expanding maps on the torus. So these maps preserve the boundary of the disk. And if the coefficient satisfies some checkable properties, we get expansion. Okay, and so if it's expanding on the circle, it's expanding also nearby. And so there's some annulus around 1, which is kind of expanded. And so that gives really good properties for the transfer operator associated to these maps acting on some Hilbert spaces of analytic functions on the annulus. These were studied, well, I guess by many, many people, but again, closest to our setting by Martin and Tichler, and really much, much closer to us by Bantlow, Just, and Slipanchuk about 10 years ago. And they were able to characterize the spectrum of the transfer operator for these maps in the autonomous case. So what we are investigating here is a case of random compositions of these Blaschke products. And for that, well, we have our driving system, sigma. We fix some annulus where all of these maps are acting. So the same annulus should work for all of our maps. And if we call L omega the transfer operator associated to this Blaschke product, then the first thing that we found was that there is a random fixed point, namely family or a function omega maps to x omega. So this is a point inside a disk of disk of radius less than 1, which satisfies this random fixed point property. So x omega gets mapped to x sigma omega by the dynamics. And this is an attracting fixed point. So in the sense that any initial condition inside this disk of radius r gets attracted to x omega, say, from the past. And this is inside this disk of radius 1, but it's important even to understand the Lyapunov exponents of the transfer operator cocycle of the random Blaschke product, because it through these formulas of the logarithm of the derivative at the random fixed point, when we average this number lambda gives us all the information about the Lyapunov spectrum. So this number is always negative. It could be minus infinity. And when that's the case, we have a trivial spectrum for the transfer operator cocycle that we denote by sigma minus infinity. And if lambda is finite, then the Lyapunov exponents for the transfer operator cocycle are just integer non-negative multiples of this lambda. Even more, we can find expressions really explicit for the top Oseledets space. So this is giving the random invariant measure in terms of this random fixed point. and quite fine information about the other Oseledets spaces. For instance, the J plus first space corresponding to Lyapunov exponent J times lambda is two-dimensional, and each of these, so one of the generators is has a pole of order J plus 1 at x omega, and the other one has a pole of order J plus 1 and 1 on x omega bar. So this gives quite a bit of information about this spectrum, and we can use all of this to construct some examples and understand some of the stability questions. For instance, if we consider the case of IID compositions of two maps, so this is going to be one of the maps is the doubling map, the other map is another expanding map of degree 2 of the circle. We can think of it in that way, but of course this is written in complex form. If we compose this in an IID way with P is the probability of composing the doubling map, then what we get is, well, what we call a phase transition. If P is less than a half, then we have a finite number lambda corresponding to countably many countable Lyapunov spectrum. But as soon as P is a half or more, we get trivial Lyapunov spectrum. Okay, and this was, I guess, a little perhaps unexpected, but for us, but thinking about this, I mean, when P is equal to 1, we just have the doubling map, right? And that one has super exponential decay of correlation. So, so this is what happens in this case. But even more surprising to us was to find that we could have collapse of the Lyapunov spectrum with arbitrarily small perturbations. So for instance, if we convolve with a normal distribution, so with epsilon width, say, what we have is that the Lyapunov spectrum of this small perturbation of the cocycle, as soon as P is at least 1/4, gets a collapse spectrum. So in particular, in this interval 1/4 to 1/2, the unperturbed cocycle corresponding to epsilon equals 0 has a full Lyapunov spectrum, but as soon as we introduce a perturbation, we get a trivial or a collapsed Lyapunov spectrum. So this was unexpected for us in the sense that this is an example of relatively reasonable perturbations where we got a collapse of the spectrum. Okay, the examples that were known where one had to work quite hard to get a collapse of the spectrum. There were, of course, examples known before. For this, probably is the same. I don't think it was a different. This is not super recent. There will be, yes, there will be some more recent, yes. And okay, so we have, then we wonder, well, can we understand better when we have stability and when we have instability? And so we were able, again, using the explicit information that we have about the Lyapunov spectrum, we were able to characterize stability and instability of Lyapunov spectrum in this family in the following way. So we have to look at the essential infimum of this derivative. And as soon as, well, as long as it's positive, so as long as we say remain away from the critical points, the Lyapunov spectrum is stable in the sense that if we perturb the transfer operators a little bit, I mean, this can be by small perturbations of the maps or in other types of perturbations, then we're going to have that the Lyapunov exponents converge as epsilon goes to 0 to the unperturbed Lyapunov exponents. And if the essential infimum is 0, then we will have instability in the sense that we will be able to find an arbitrarily small perturbation which has a trivial spectrum. So this is quite complete characterization of stability in the case of Blaschke product cocycles. Then as a corollary, we were able to show that if we put some distance in the space of random Blaschke product cocycles, then we can show that stable Blaschke product cocycles are topologically generic in the sense that they form an open and dense set. Then with Joshua Peter, we asked the question, can we say something about measure theoretical genericity? Okay, so can we understand this in some way? And so far, the result that we have is about stability, but in the context of Blaschke product cocycles, which fix the origin. So this is a specific case. It's important because we can always conjugate random Blaschke product to a random Blaschke product that fixes the origin, but at the moment, the result is only for this case. And so we have a similar setting as before. We have random Blaschke products. So we start with such a random Blaschke product T. We can have variable degrees, for instance. And the perturbations that we introduce are basically shifting the zeros. So these zeros are inside the unit disk. So we just go to the complex plane, shift by gamma and come back. So that's our perturb. Those are our perturbations. And what we were able to show was that in the case where omega is the circle and we have a C1 map, so the coefficients or the zeros depend in a C1 way of omega, then we have that for almost every perturbation, the perturbed cocycle will be stable. So that's the state for Blaschke product cocycles. And in this next example, what I want to tell you about is another example, which is going to be about piecewise expanding maps of the interval, which are what we call random metastable maps. So metastability for us means, well, generally what metastability refers to are systems which have two or more nearly invariant components, or thought in another way, there are two or more components where typically trajectories spend a lot of time before switching to the other component. And Keller and Liverani gave a definition in the context of transfer operators, and again in the autonomous context, and they called metastable systems those that have a second eigenvalue which is near 0 but not equal to 0. So similarly, we call metastability in the random case where the second Lyapunov exponent is near 0 but not, sorry, in the case of autonomous systems, the eigenvalue is near 1 but not equal to 1, and in the case of random systems, metastability is the second Lyapunov exponent is near 0 but not exactly equal to 0. And again, a simple example is a two-state Markov chain. As before, if we have transitions given by epsilon1 and epsilon2, where these are small, well, typically trajectories will spend a lot of time on each of the components before switching, and then spending a lot of time in the other component, and so on. And in this case, we can also compute the Lyapunov spectrum. So the leading Lyapunov exponent is 0, corresponding to preservation of mass. And by looking at the determinant, we can get exactly that the second Lyapunov exponent is given by this integral of log of 1 minus epsilon 1 minus epsilon 2, which of course, if epsilon 1 and epsilon 2 are small and close to 0, but not equal to 0, we get this metastability. So the model we looked at in the case of interval maps is called pertent maps, and it was studied by Horan in his thesis. This is a family of maps which has two parameters, A and B. These are maps of the interval -1 to 1. So B measures how much above 0 this tip gets mapped to, and A measures how much below 0 this tip gets mapped to. And of course, when A and B are 0, we have a system which is not ergodic. It has these two invariant components, and it preserves two. So Lebesgue measure on the left and Lebesgue measure on the right are invariant. But as soon as A and B are positive, there's a unique invariant measure for the system. And this is what we have been studying. And in the case of random metastable maps, well, A and B would depend on omega. And on top of, so we will fix A and B, saying how these tips move up and down with respect to omega, and then add epsilon, which is a parameter saying, how much are we going? So scaling this A and B. And we're going to see what happens for epsilon small. What Horan was showed in his thesis is that so that there's an upper bound for the second Lyapunov exponent of order epsilon, and he also had some estimates on this constant C given by cones, and the first Lyapunov exponent is of course 0. So with Anthony Quas, we studied this exactly the same model, and what we were able to show was an approximation up to order epsilon to the second Lyapunov exponent. So this is minus epsilon times this integral of A plus B, these leaking quantities. And the error is of order epsilon squared log 1 on epsilon. And the rest of the spectrum is far away, so it's pretty much at minus log 2. So that would be giving us a random metastable system. So let me tell you a little bit about how we showed this result. And before that, just connect with the case, the simple case of 2 by 2 matrices. So if we write these matrices, which are kind of naive approximations to the system, and if you're familiar with the Ulam scheme, they are giving us what the Ulam scheme would give us as approximation to the system when we use the coarse partition into interval on the left, interval of the right on the right, up to epsilon squared error. And here, well, we said this, we can compute these Lyapunov exponents, and by Taylor's theorem, well, we get pretty much the same quantity up to our errors. Okay, so it's a good approximation in this sense. But how can we show rigorously that this approximation? So we start with a small epsilon, for instance, less than 1 on 2000. We look at the whole, so we say the points in phase space which switch from, say, left to right or right to left in one step. That's what we call the holes. And what we have in this case is that if a trajectory falls in the hole, so it will remain on the other component for at least something like log 1 on epsilon iterates. And so we choose k, so that, 2 to the k times epsilon is between 1 on 8 and 1 on 4. And we know that trajectories will not come back to the same interval, or any 2 visits to the hole are separated by at least k steps. So this is what we use in bookkeeping process that we call the quarantine approach. So the idea is we are going to keep track of densities, not just as just the single, say, bounded variation function, but we're going to split it depending on how far in the past it has gone through the hole in the following way. So we have k+1 components. We're going to think of F0 as a part that is not in quarantine, and F1 and so on will be the stages through quarantine, and then after Fk, the density will come back to the outside world. And more precisely, the transfer operator that we define in this space will be as follows. So the part of F0 which is not in the hole will be just pushed forward, and also the part that was in the last stage of quarantine will come back. Whatever goes through the hole will be sent to quarantine, to the first stage of quarantine, and all the rest will just be pushed along the quarantine process. So whatever was in the first stage will be pushed to the second stage, and so on. So that's the transfer operator here. Of course, if we want to keep track of a single density, which is just the sum of all these pieces, we just have to add all these pieces, and there's this commutative diagram. And the reason why this is useful is because we have an invariant set, which is consists of nearly constant functions outside of zero. So variations 0, see here, means the variation of the function except for the jump at 0. If we start with a small variation and also decaying variation along these steps, and also small and decaying norm, L1 norm along these steps, we have an invariant set. And that's useful to approximate the Lyapunov exponents in the following way. So if we start with a function and we just call phi plus and phi minus the amount of mass, total mass that is in the left or right interval, then what we get after pushing forward is just a direct computation to get that the integral on the left or on the right is just whatever it was before, minus what has gone through the hole, plus what has come in through the other hole. And because the measure of the holes is given by this epsilon A and epsilon B up to epsilon squared error, we get estimates on how much mass remains on the left and right intervals after one step with some error, control error. And if we look at functions with integral 0, this is also an invariant set. And in that case, this estimate becomes a multiplicative estimate. And so we can iterate that and get that the mass on each of the components decays with this rate that we can approximate using Birkhoff's ergodic theorem. And so we get an upper bound for the L1 norm of these functions given by this epsilon times the integral plus an error term. So that's an estimate for the L1 norm. Of course, we need to estimate also the bounded variation norm to get metastability, say. But, well, that comes from, say, the Lasota-York inequality. If we have something outside the essential spectral radius, the two rates, the growth rates will be the same. And because we can decompose a function of bounded variation as a sum of two functions in this invariant set, we get an upper bound for the second Lyapunov exponent. To get a lower bound, we just find a function which has this given decay, and that's the sine function. So we start with the sine function and zeros everywhere else. And in that case, we get an estimate on the L1 norm of this function, which is given precisely by this product of 1 minus epsilon A plus B along the orbit of sigma, and so we get the lower bound, which is exactly matching the upper bound up to this term of order epsilon squared log 1 on epsilon. So that's the result for the second Lyapunov exponent. Now, for the rest of the spectrum, what we have is we can construct functionals so that, and these are, of course, omega dependent functionals, so that if we start with a function which has integral 0 and functional also equal to 0, then the growth rate will be very close to minus log 2. So we'll have an upper bound, which is very far from 1. And so that gives that if there's a third Lyapunov exponent, it will be bounded above by that quantity. So all these calculations that I've showed are quenched in the sense that we have done calculations omega by omega. But if we want to really put this in the context of multiplicative ergodic theory, we have to give this some context. And so we can do this in the case of functions of bounded variation. If we have that the number of maps that we are composing is countable, and that's one of the original results by Froilen, Lloyd, and Quast. But if we want to allow, for instance, to compose at most, say, more than countably many maps, say maps indexed by some one parameter family, we need to consider more different functional spaces. And we can do this in this context using these fractional Sobolev spaces that were introduced by Roberto. And the price we pay for that is that we have to give up a little bit of room. So now, say for the third Lyapunov exponent, we wouldn't have that epsilon bound, but arbitrarily close to minus log 2. So I think it's not too much to give. And what we gain if we do that is that, of course, we don't just have an omega-wise decomposition or omega-wise statements, but actually this multiplicative ergodic theory. And for instance, we get measurability of these first and second Oseledets spaces, for instance, as functions from omega to L1, and also measurability of the multipliers that we get along the orbit. And another reason for us to really try to get this connection with multiplicative ergodic theory was that this work was published in the volume celebrating the 80th birthday of Oseledets, which is with me in this picture several years ago. So I'll just leave you with a summary. So random dynamical systems, I hope I convince you, give us some quite general and flexible framework to study systems which have influences from random to seasonal effects. And multiplicative ergodic theory gives us some spectral type decomposition, namely Lyapunov exponents and Oseledets spaces, which encompass fundamental information about transport and statistical behavior in such systems. And finite Blaschke product cocycles give us examples where the transfer operators Lyapunov spectrum can be rigorously analyzed, so we can really characterize it and understand stabilities and instabilities in that context. So both happen, but stability is generic. And in the case of pertent maps, this is a class of random metastable maps where we were able to approximate the first two Lyapunov exponents. So thank you for your attention.
Questions? have a question. So you mentioned these instability results by Bocchi and then Bocchi-Viana. Are they of the same kind you showed with the collapse of the Lyapunov spectrum, or is it something different?
So their examples are for matrices, and I think all the examples are collapsing the Lyapunov exponents to 0. So I think these are determinant 1, say, cases. So it's a different different phenomenon.
More questions?
So in the Blanchett product thing, you have a very explicit formula for the Oseledets decomposition, if I understood. So in this case, do you have something about the simplicity of the spectrum in this case?
So let me find it. So yes, so we know that the 0 is simple, but all the other Lyapunov exponents have multiplicity 2.
Okay.
And yeah, we don't have exactly the expressions for the, say, spans of these 2 vectors, but we know quite a bit about them. We know, for instance, one of the vectors has a pole of order j+1 at x omega, and it's the only pole, and it's so it's in this in the space spanned by this, and something similar happens with the other. So there's some sort of symmetry there that gives this multiplicity 2.
I see.
There.
Thank you.
Okay, more questions? So if not, we thank Cecilia again. Okay, and we proceed with Sandro Vaienti, and he will talk about Poisson statistics for quench dynamical systems.
Thank you very much, the organizer, for inviting me. It's always a pleasure to be here. I apologize, there's a mistake in the title here. I realized I did too late. It was too late to change it because I sent yesterday night to the people here. Okay, so now I will present 2 parallel work on the same subject, which is to determine compound Poisson statistic for quench dynamical system. You will see there are two approaches, a little bit different in the technique and also in some assumptions. Okay, the first is a paper which 2 papers in preparation. The first with my student Lucas Amorim and Nikolai Haydn, who is here, and the second is with my Australian friends, Jason Atkin, who is not here, Gary, and Cecilia. And both papers are based on our previous work. The first paper with Nikolai Haydn is based on 2 works I did with him and other collaborators, where we considered the problem in the deterministic setting, and we developed some techniques which then we are trying to extend to the quenched case. The second paper with Cecilia and Gary and Jason is based on what Gary explained to us 2 days ago. But in fact, what I'm going to tell you today is just the following of what Gary introduced. What Gary introduced was, if you know, the level 0, which is the extreme value theory. I'm going to the higher level, which is the compound Poisson. I will explain to you what I mean briefly very soon. Okay, so these are just the contribution I'm going to present today. The motivation is very simple. The problem is very simple. It's a very basic problem in recurrence theory. So you have some set in the phase. Okay, now this transparency is about, just to introduce the problem, is about the deterministic situation. So you have a set H in the phase space, a small measure. This measure will go to 0 at the end. This is called also a rare set or an extreme events. And we have some states or some trajectory which enter in this small set. And what we want to compute is the probability that this trajectory or this state spend some time into this set, but we want to compute this time having considering the trajectory on a prescribed time interval. I will write the formula in a moment. And okay, just for the sake of simplicity, for the moment we consider the temporal evolution given by a map T acting on some space M, which preserves some measure, I mean, usual setting, which were presented in several talks here. And in particular, the rare set H will be indexed by some number n, and when n goes to infinity, the measure of this set will go to 0. Okay, this is very rough introduction. Okay, let me be more precise. So, in order to make sense of what we are doing, it turns out that the choice of the set cannot be independent of the time n we are looking to the state of the system. In particular, in order to get something interesting, we have to take some scaling for the measure of this rare set. In particular, we have to fix some parameter t, which is a positive number, and the measure of this small set, from now on I will call it a whole, should verify should verify equation 1, which can also be stated asymptotically. But for the moment, let's suppose for each n we can find a set, a small hn, which verify this property. And this is true in particular if the measure is not atomic and hn is a ball, because if mu is not atomic, the measure of all is continuous in the radius of the ball. And then what is the quantity which we are going to introduce is this one. So I compute, I look how many times the trajectory of the point stays into this all hn when I iterate the orbit until this time t over mu of hn. And this time mu of hn is called the Katz time because it's the right way to normalize the recurrence property, as you will see in a moment. And what we want to compute is this distribution. So it is the probability that this number of time I visited my hole when I iterate the trajectory up to the Katz time is equal to k. And the question is does this distribution converge to some limit law, in particular weakly? And this is exactly what we want to do. And I presented it for the moment in the deterministic setting. Now let's go to the random setting. I can go fast here because there are already been several talks where people introduce and detailed what a random system is. In this case, the random system will be a quenched random system. So I have some map T. So I have some driving system which is called omega with some measure m, which is ergodic, provided the shift map of sigma is invertible, or sigma is not necessarily a shift map, by the way. I will give you an example just below. And then we consider from the interval E to itself a map intersect by omega, T omega. By the way, one could be more precise. Instead of defining T omega over some interval, we can define it on fibers. But in this case, we can identify all the fibers with the interval itself. And then we go to the random composition, okay? And this is also in Cecilia talk, there was this composition of maps. Two examples, and because this example will be used in the example at the end of the talk. One example is if we take sigma as an irrational rotation, which verified the assumption of a driving system, and we take omega, we define omega in a finite number of elements. On each element, for each element, we associate as we want some map T. I will tell you at the end what are the properties of this map T omega. And then when we move omega into this partition, provided we fall into some of these partition element, we associate to it a map. And so these are the composition of the maps. Very simple. We will use it in an example at the end. This example is very simple, but it shows you that this sigma is simply ergodic, not more than that. And this is enough for what we are going to do. The other example is much better from the point of view of ergodic properties of the driving system, because we have just a shift space with the Bernoulli measure. And in particular, what we do is we take a finite number of symbols. To each symbol, we associate a map. The regularity of the map will come at the end of the talk. And then what happens, we associate to an infinite word just the first, the zero symbol. So when we compose the map, we are just following the letter in the infinite word. So it's particularly simple to construct the orbit. And then we consider a random observable, which depend on omega and on the point x. Gary, 2 days ago, explained it very well why this, I mean, the two kinds to look at this random environment, just looking to observable defined on the ocean, having in mind, I mean, long averages, or just if one was interested in fluctuation of local fluctuation. So I will not go into detail here because he really explained it very well, this kind of choices. Okay, and as usual, these are the transfer operator defined for this quenched system with some general potential g omega. Okay, zero means that we are considering this system without perturbation, because I will introduce the perturbation later on. So we call this kind of system closed, because you will see the perturbation which we are going to introduce will open holes in the system. But okay, this is the reason why we have zero. Then we will get epsilon when the trajectory and the operator will be perturbed. Okay, so this is nothing new. Okay, we have the operator and we have the potential, which is g omega 0. At the end of the talk, I will show you also the assumption of the potential. And then this is the iterator of the operator. Okay, this is the operator. Okay, all these have been seen several times. And to finish this presentation of the random system, just two things. First of all, we need some probability, even in the quenched setting. The probability will be what we called the equivariant measure, mu omega. Mu omega verify just this property. This is the equivariance property in the quenched setting, which is more or less what mimic the invariance for the deterministic dynamical system. How is this co-equivariance measure being constructed? In the usual way, namely, we take the multiplier for the operator and for the dual, and with this we construct the measure mu omega 0. Okay, so you see this is the operator and this is the dual, and this gives us the conformal measure, and this gives us this multiplier, which is the maximum, the top eigenvalue for this operator, and with this we construct this measure. Okay, as Gary said 2 days ago, it takes us sometimes in order to get this construction, in particular to get this conformal measure, because the system we consider it where system, even if the system on the interval, but with a lot of discontinuities, and okay, it needs some work in order to construct this object here. Another important point, because we are going to apply a perturbation result by Carlanger and Keller, is the quasi-compactness of this operator, which is this one. As you know, we already saw this formula several times. And in particular, we need also this quasi-compactness property for the perturbed operator. Okay, so this is a brief account of this kind of quenched system, which will be the main system to which we are going to apply to determine this Poisson statistics. Okay, now, as I told you, there are two approaches in order to get this result, and these approaches, in some sense, needs to focus on two different ways to look at the process itself. Okay, what we have to handle with is this quantity here, namely. Okay, now I take the trajectory which jump from one fiber to the other, and I have on each fiber I have some hole. Okay, so you have to imagine we have here holes which are, because this is different copies of the interval. On each interval, we have one hole. On each copy of the interval, we have one hole. So they all are indexed by omega, sigma square omega. Okay, and now this trajectory is also a composition of maps. So basically, if you are in omega, the map send you in the fiber on sigma omega. And Tj omega means exactly this composition of maps. So basically here, they all are moving with the random in the random environment. And so this is the reason why you start from here, but you jump in the other holes. Now the question is, if we want to define this object here, I have to decide what is this n, because I mean, we cannot. Okay, it's important that this n here is related to how many times I iterate the system itself. I mean, you iterate the system n times, right? But at the same time, we need a relation between the number of times you iterate and the number we are looking to the process itself. So there are two different approaches. The first approach is the following. I put holes on my fibers first. These all are called h omega epsilon because epsilon is the size of the hole. For the moment, the hole is, okay, here I wrote h omega as a set of zero measure, in particular of mu omega zero measure. But now I take a neighborhood of this hole. This is a real hole. This is a set which is a null set, as we call it, but this is the hole, right? And what I do is I put holes on the fibers, and then I integrate these holes against the ergodic measure on the driving system. And this defines a number, n. Okay, so first I choose the hole, I put the hole on the fiber, I take the average of this hole, and I fix the time n where it is a positive parameter. And then I construct this sum. So in this first approach, the hole are chosen, fixed, and then it defines the time I look into the process. And then, as I said to you before, I want to know what happens when the size of this hole goes to zero. This is the first step. Yes. No, epsilon is, okay, in this first approach, epsilon is a number which is fixed for all the holes. Yes, epsilon is fixed. It's just a neighborhood of what I call h omega here, which are sets of zero measure with respect to mu omega. What? N is defined in this way, so it's completely deterministic because now you are integrating, you are integrating on omega. This is the first approach. The second approach is this one, where we do the other way around. So I fixed n from the very beginning here, and I choose the hole in such a way as I verify this assumption here. So I fix n, I mean the time interval into which I want to look at what is going on, and then I choose the hole in such a way that this is true. And again, we require this for any n because we can always play with these error terms in order to get this equality satisfied. And in particular, here we allow this parameter t to be random. Instead, in the previous approach, t was not random. So there are, okay, of course, there are similarity, and one could go in some sense to one to the others, provided one puts some additional assumptions. But conceptually are not exactly the same. And also the technique will be different. And the reason why we use these two, it depends also on the technique I'm going to use. I will tell you in a moment what the techniques are. Okay, so now let's continue. Okay, first of all, now let me tell you something about what we want to prove. Then I will come back to what Gary said 2 days ago to fix the problem. We want to prove convergence to what people call compound Poisson. But what is a compound Poisson statistics? Okay, here is some information, probability information, if you want. An integer value random variable is called compound Poisson if you can write it in this way as the sum of IID random variable xj up to a random variable itself, which is independent of the xj, and which is Poisson distributed with parameter t. Okay, so this is the definition of compound Poisson. Of course, you can get a lot of distribution according to the regional distribution of the xj. And the xj are independent with the same distribution, and the distribution of the xj is called lambda L. In particular, if we have only one xj, which is equal to 1, and all the lambda L are equal to 0, you recover the Poisson distribution. There is another important compound Poisson distribution, which is when these xj are distributed according to a geometric law. So the lambda L have this form. And in this case, the theta is the parameter of the Poisson here. And you have the distribution of this discrete random variable. Or people call also this mass distribution, but it's exactly the distribution of the random variable. But these are two important distributions, which we find in our example later on. But what we are going to use is another characterization of the compound Poisson, which is the following. There is a result in a Feller book or in Lukács' book on characteristic function, which shows the following. A random variable W, which is discrete and positive, is compound Poisson if and only if it is infinitely divisible. And infinitely divisible means two equivalent things. The first, you can write it as the sum of IID for any n. You can write it as the sum of ID random variable defined on the same space. Or, which is exactly what we are going to use, the characteristic function of an infinitely divisible distribution can be written in this way. Can be written in this way. So where you have the n power of other characteristic functions. And just because we are in Italy, let me tell you that the notion of infinitely divisible distribution was given by Bruno De Finetti. And he also proved a very deep theorem on infinitely divisible distribution, which were then developed by Feller, by the Russian school, by the French guy, by Levy in France, and then by Kinchin, and so on and so forth. But infinite divisibility was first of all introduced by De Finetti here. Okay, now a few some words on the previous contribution. Yes. What I told you before, this random variable. This is a random variable. And you want to, okay. But now I will give you all the detail. Okay, so yes, just a few words about previous contribution in this field. I mean, as far as I know, the first two papers which dealt with this kind of argument, Poisson in particular for dynamical system, was paper by Piskel and Dirata in '93. And 2 years later, we saw Dirata in Marseille. We began to work on this problem. And okay, here are a list of people who worked on this stuff. And I tried to collect the people according to some affinity. I didn't put my name here and my name and the other collaborators who are here, but because they are here. Then, for instance, with Nikolai, we did some work on this topic. Then Nikolai continued with his collaborators. And then Abadis, Sol, with Françoise and Müller also have a strong contribution in this field. Then there is some other work by Kiefer and his students, fundamental work by Collet Chazot, where they looked at this problem for the Enon map. And then I will tell you in a moment why. A few years ago, people working in extreme value theory came into the field. And these are the bunch of people who gave contribution in this field. Then following a work by Carlangelo and Keller wrote another fundamental paper in this domain where he introduced the spectral operator, which was one of the two techniques which I'm going to develop. And I also learned recently, Bunimovich also entered the field with some trying to get the Poisson statistic, but using some other technical approach. But I don't know very well what he did. I didn't look carefully to what he did, and probably I forgot someone. But now let me explain something on the blackboard, because I want to make the connection with what Gary said 2 days ago. So basically, suppose you have no, because I told you these people work on the extreme value theory and there's a connection. The connection is very easy to establish. Okay, so suppose you have a function phi which goes to infinity, phi, okay, around some point. So you fix some threshold u, right? And then, okay, you have some probability which is stationary here. So suppose you have an invariant measure p. And then, okay, then you look at this object here, the probability that, okay, now I define all, the all Hn is the set of all the points where phi of x is larger than un, right? So this is the all for me. And now people in extreme value theory look at this, the probability that phi is less than un, this threshold, phi composed with t is less than un, up to phi composed with t minus n minus 1 x, okay, is less or equal to un. Okay, this is what people look. But this is exactly equal in our case, the probability that x is in the complement of Hn, t of x is in the complement of Hn, up to t n minus 1x is in the complement of Hn. Okay, the same stuff. Well, this is the first observation. The second observation is the following. Okay, consider now the following event, which is exactly written here. So x is in the complement of Hn up to Tn minus 1x is in the complement of Hn. Look at these events, okay? And now take T minus 1 of this event. So you take the preimage of this event, and this is exactly equal to another quantity, which I'm going to define in a moment, all the point x where tau Hn of x is larger than n. And now let me define what tau Hn is. I will do here. Tau Hnx is the first time the orbit enter Hn, which is called the eating time of the set Hn. Okay, this is just very simple observation. By the way, the first who did this very simple observation was Pierre Collet, probably 15 years ago, right? And you see immediately that thanks to this observation, right, the measure of this guy here by invariance will be exactly equal to the measure of this one, right? So basically, you compute the distribution of the maximum of this observable exactly by computing the statistics, because of the distribution of the first eating time. But we know this. I mean, we knew it because we worked on it just before people coming from extreme value theory enter the domain. And this guy here, I put this because it depends I mean, the result is not always what I'm going to write, but this guy here, when n goes to infinity, behaves like E minus theta t, where t is just normalized in this way. Where n is just normalized in this way, t divided the probability of Hn. So again, we found this this normalization here in order to make sense to this convergence, right? So this was proved by several people, and several people also worked on the determination of this number here, because this number here depends on the choice of Hn. Generically, this number is equal to 1, but not always. And then people coming from extreme value theory, they also provided techniques in order to determine this number of theta. But I will show in a moment how we can compute rigorously this theta even in the quotient setting. Okay, so but you see, this make the relation between this guy here, which was studied independently of extreme value theory, and this one. And now, just a final observation before going to this what I want to show you. If you define this observable here, I call it n, and nx, which is the sum j from 0 to this normalized time, the probability of Hn and you put here the characteristic function of Hn Tj of x. If you define the observed, the probability that this guy is equal to 0, I put k equals 0, is exactly, by definition, look at the definition of this object here, is exactly when n goes to infinity equal to E minus theta t. For this reason, I said the extreme value theory, which Gail presented 2 days ago, is the order 0 of what I am going now to present. Here we go to the higher order. Namely means we take k larger than 0 here. And so we have something complicated here, which would be exactly what I call compound Poisson. This is exactly the goal of what I want to do. Okay, now let's go into the detail. Okay, now since there are 2 approaches, let me tell you about the advantages and the disadvantages of the 2 approaches. In the first approach, which I developed with Nikolai, what we can prove is we have a convergence. Okay, what we prove is the convergence of this in distribution to a compound Poisson. But the compound Poisson can be written in this way. Okay, and these variables are defined, I'm sorry, Marco, but on a probability space, which is not probably the probability space at the beginning. And but still, we can identify the xj. The distribution of the xj can be determined in terms of the distribution of object in the original probability space. We can compute explicitly. We don't have this in the other approach for the moment. But the other advantage is the correlation are not necessarily exponential. But the disadvantages are the convergence will take place, convergence when epsilon goes to 0. The convergence will take place along subsequence. I will tell you why. And the driving system must be more than ergodic. I will explain you why also. In the second approach we developed with Cecilia, Gary, and Jason, we only need ergodicity for the driving system. The convergence is given for any epsilon or any n, because here we we consider n as a parameter which we send to infinity. Instead, for the moment, we don't have an explicit representation of this object here in terms of quantities which can be analyzed before going to the limit explicitly. And also we need the spectral gap for the operator, because we are going to use a spectral technique. So we need the curve correlation in some sense of exponential type. Okay, these are the difference between the 2 approaches. Okay, let's go to the first approach. Okay, there are a few assumptions in the first. Okay, my goal today is not to give all the definition of the maps and all the assumptions. It's just to present these 2 techniques. At the end, there will be anyway some example and the presentation of property of the map. But in this first approach, what matters is the decay of double decay of correlation. First of all, for the measure mu omega, which are this equivariant measure along fibers, but also on the measure on the skew system, which is generated by this random system, because to each pointed system we can associate a skew system. Okay, so in some sense, this measure here is the measure on the skew system, for which one of the marginal is the measure on the driving system, and the other one are the measure on the fibers, which are called conditional measure. We need also the curve correlation for this second measure, and this requires mixing for the driving system. For this reason, this technique does not require exponential decay, but they requires the mixing on the driving system, which we don't have with the other technique. And okay, and then yes, no, here it is written. We have either exponential decay or polynomial decay with some exponent p, which must be related to the other quantity which enter, and this depends on the particular example you have in order to determine this. Okay, now I told you before that the variable in the compound Poisson living on another probability space, let's say, were related to a quantity which can be computed before going to the limit concretely. This is the reason. So basically, I construct here the sum, always the same sum. I count how many times I visit the holes along the fiber. So this quantity here are related exactly to the problem itself. And then I take two double limits, which are written here. Namely, first of all, I take the limit when epsilon goes to 0, and this limit is required. But even in the other approach, there will be some requirement, the existence of some limit. Everything is not, it doesn't hold for I mean, always all this. We require the first limit in epsilon, thereby monotonicity of the quantity involved in the theory. The second limit in L, which is, I just look at blocks of recorded time into which I'm looking to the number of times I visit the set. This number L is fixed. I go to the second limit. And so this defines a number, lambda L, which depends only on this L here, which is the number of time I jump into the set L time. Well, then we have this theorem. This theorem tells you the following. When epsilon goes to 0, I go to tilde pi L, which is exactly a compound Poisson with the distribution of the Poisson, which is P in the sum, is given by this number here, where the lambda L are just given by this formula here. And the distribution of the xj, this variable, right, are living on some probability space, are given exactly by this number here. So we wrote the compound Poisson in such a way that we can recognize the distribution of the variable involved, because they are related to quantity which we can compute before going to the limit in this way. A few words on the technique of the proof. The technique uses a very beautiful theorem by Nicolai, who is here. I think this result is also interesting intrinsically, because basically, if you have a sequence of random variable xn, which can be 0 and 1, our random variable are 0, 1 because are characteristic function, and you take the sum up to n, then you can approximate this variable with the sum of other variables. Here are the details, which are constructed in this way. You take some blocks of length L, and the sum of the variable in the blocks n will have the same distribution. Is written here. Okay, here, look. Z tilde j are independent random variable, which will have the distribution of the block constructed with the original variable of length L. And then you look at the difference between the two distributions. So I repeat, here you take the sum of IID random variables, and the distribution of the variable entering the first sum, the second sum, sorry, are the same of a suitable sum of variable which belong to the original sequence. And then you take the error between the two. And what is interesting is the error between the two have this form here. It seems difficult, but working a bit, you will see that this can be, if you have good statistical property for our original system, can be computed. For instance, briefly, R1 deals with the curve correlation. You see the correlation here. R2 and 3 deals with what we call short returns, to look at the short returns. And this quantity here can be worked out. In particular, what we did, we applied this in our situation. And what we get was exactly this quantity here, R1, R2, R3, which could be computed explicitly. Let me tell you something about one of these quantity here, because in one of these quantity here, what we meet is this sum here. And this sum here, we have to send epsilon to 0 in this sum here. So n is fixed here, we have to send epsilon to 0, if you remember. But in order to handle with the object here, if you want to send epsilon to 0 and epsilon is into the sum, we have to use a Borel-Cantali argument. And this Borel-Cantali argument works if epsilon is chosen according to a sequence which is summable. This is the reason why at a certain point we introduced the choice of a subsequence in order to get the limiting law. Okay, this is the first approach, using just only probabilistic tools, and with the advantages and the disadvantages which I show you. Now let's go to the second one. Okay, the point is we applied the spectral technique which originates from the work of Carlangelo and Keller first to get the extreme value theory, what Gary explained it to us 2 days ago. And for at least 1-2 years, it was not clear to us if we could extend this to the Poisson statistic, namely to the higher returns. And now it turns out that it is possible, and I will show you. Now, here is pretty general what I'm going to present now, because this technique works not only for transfer operator, but also for operators in other situations. For instance, if you have Markov operators, and the operators is just, even for stochastic differential equation, this works. We applied it just in a recent work with Stefano Galator, Franco, Flando, Paolo, who is here. We applied exactly this strategy here. Okay, well, how does it work? Here is for the deterministic system, because it's very simple to present, and then I will go to the random one later on. So we have this sum here, Again, I take n using this scaling, and then I construct this sum, which is exactly the sum into this parenthesis here. For the moment, k is not equal to n, but then we put k is exactly equal to n using this scaling here. And what I do, I compute the characteristic function of this variable. That's it. It's finished. So I take the characteristic function of this variable here. The probability space is just given in this case by the invariant measure mu. Okay, now if you do so, first of all, we have a transfer operator from the beginning, which is L. Suppose think to a map of the interval for the moment, which preserves some measure mu with density h, right? Write L the operator of this map, and now I define a perturbative operator in this way. So I take L applied to the e to the power s time the characteristic function of the whole. More or less, what we do when we consider twisted operator. It's very close to it. But for the twisted operator, the perturbation is smooth. For this reason, we use smooth perturbation theory. Here is not smooth. So we have to use this singular perturbation theory by our friend here. And now you iterate this operator k time. It comes to iterate the k times the unperturbed operator by applied now to this exponent, where now we have the Birkhoff sum of the Sn. Okay, so along the orbit. And now, very simple observation: the characteristic function of Snk, I remind Snk was exactly this object here, right? Is exactly equal to the k power of this perturbed operator applied to the density. Okay, let's see. So since we have this, now we know what to do. But before showing you the computation, there was a paper in 2020 by Zhang, where he applied the same spectral technique, but not taking the characteristic function, but taking the Laplace transform. No, wait a moment. I know Laplace transform is very close to characteristic function. Instead of S, you use IS. So it's basically the same. But he only did a part of the work. So he developed the theory only to get standard Poisson. He didn't go to compound Poisson. And what we are doing here is, I will show you that all the limiting variables which we get are compound Poisson. This is interesting, I think. Anyway, we do it. Now, we have this technique by Calangio and Keller, which was also reminded by Gary. So I will not go into the detail because we saw it at least one or twice. So basically, the idea is to get an asymptotic development of the top eigenvalue for the unperturbed operator in terms of the top eigenvalue of the perturbed operator, which is given by this formula here, where this number theta s comes from this expression here. And in particular, theta ns is just the closeness in N1 of the two operators, and theta s is given by this formula here, right? And this formula here seems complicated, but it's not, because if you look at this object here, basically what we are doing is we take a hole, we look a point on the hole, and then we require that after n times, k times, sorry, the points come back to the original hole, but in the meanwhile, they could come back even L times. Yeah. So basically, I'm looking at points which are the beginning in the hole, come back surely after k time, k plus 1 time, but they could also stay in the hole in between. But they must be at the beginning and at the end after k plus 1 time, plus sometimes in the beginning. And this quantity can be computed on examples. Okay, so with this, what we get is simply the result. So basically, you do the computation, And you get this limit of the characteristic function is given by this number here. And this number now, what can we get from this computation, which is very simple, provided one verify the previous asymptotic expansion? Well, first of all, this is the limit of characteristic functions. Is it a characteristic function? Yes, if it is continuous in 0, and it happens. Okay, so first result, it is so the converge. So we know there is a random variable for which this is the characteristic function. But this random variable, what it is? Let's continue. Now you show that this is infinitely divisible, and the proof is not one line, one formula here. You take t divided by n, and you take the exponent of n. Finish. This is infinitely divisible by definition. Moreover, it's very simple to prove that this random variable is the limit of discrete positive random variable, so it's discrete also. So now there is result in Feller and Lucas with the following: if z is non-negative integer and it is infinitely divisible, it's a compound Poisson. So this characterizes completely all the limiting distribution being compound Poisson. Moreover, it's not finished because we have characteristic function. How can we come back to the distribution? Since the limiting random variable is discrete, we can apply Levy inversion formula. Very simple, which is this one, right? The point is this sometimes it's not easy to get this limit. In some cases we can. I will show you in a moment. But this is a general philosophy. Okay, so this is okay, this is exactly how this works. And give me two examples, because even if this is in the deterministic setting, it's very elegant, and we can recover immediately a result given by other contribution. For instance, suppose we have a point x0, which is not periodic, and we have sequence of O's. This is still the deterministic situation, shrinking around this point. The quantity beta, which are written here, can be computed using some continuity argument, as in the other contribution, by the way, can be computed very easily. And we get that the characteristic function we get at the end is this one. But so you open a probability book, and you will recognize immediately that this is the characteristic function uniquely associated to the standard Poisson, E minus k tk over k factorial. Finished. Now take a periodic point of period R, less larger or equal to 1, do the same computation using exactly the same argument, using the other contribution, using continuity of the map, distortion, whatever you want, but exactly the same setting. You prove immediately that the characteristic function is given by this, by this. So again, open the book, and you will see that this is the characteristic function which is associated to this mass distribution, which is exactly the polyhyper distribution. And okay, but in this case, you can generate a lot of other examples. Let me give you only one. I'm sorry, which is just I should have another one. Oh no, it's at the end. I will show you at the end in the quench setting. But even in the deterministic set, you can play now with this, because you can take points which are periodic or aperiodic. All this computation can be done. At the end, what you get is characteristic functions, which are mixture of different characteristic functions. So we don't know what the distribution is. But it's more or less what happened with the stable laws. You know, we have the characteristic function, but it's difficult to come back to the distribution. Here is more or less the same. Okay. Briefly to the random case. So in the case of the random case, okay, all the quantity can be translated into this setting again, right? So now the O's move along the fibers, and the maps are composition of maps, but the operator more or less behave in the same way. So with 0, I have the unperturbed operator. I apply it n times to the Birkhoff sum given by this this sum of characteristic function as before, and then okay, here is the scaling which I told you we are using here, where we fix n and we adjust the all suitably and accordingly, and then we get this theorem here, where exactly using the strategy of the deterministic setting. Of course, there are much more work because it's random. but the idea is the same. And at the end, we get this characteristic function. It's a characteristic function because with the summability condition we put on the choice of this beta, this function well defined is continuous in zero. So it's a characteristic function. In particular, this theta s, which enter the integral, is given by this quantity here, which is again related to this object here. But this object here are objects which are in terms of sorry, this is the next example. This object here are objects on the closed system, so they are computed without perturbation. This is interesting. Just an example to finish. Let me come back to the example Gary presented a few days ago. This is a map. We can play with this map in different ways. I will give you 3 examples of what we get. In the first example, the map moves, but all this map preserve this periodic point. Sorry, they preserve, yes, all the map has the same fixed point here, but the slopes moves for all the map. In the second example, the maps moves because they are random, but the central branch will be the same. And then in the third example, I will take 2 maps moving with some probability chosen according to a Bernoulli shift. Okay, first example, the map are chosen as you want, provided the slope are linear, because we want all the conformal, all the equivariant measure be Lebesgue to simplify the computation. And the driving is a rotation. For this reason, I introduced the rotation at the beginning. Well, in this case, you get this result. And this is the characteristic function. And it's not the characteristic function of a standard Poisson, neither of a polyhedral. We don't know to what distribution this is associated, because it's really difficult to apply Levy formula to come back. But it's a general distribution. It is. The second case is easier because in this case we have okay. Okay, no, there are only 2 examples. Okay, the other one is okay, no, only 2. In this example, I take 2 maps, right? And I choose 2 maps according to probability P1 and P2. So I put on the driving system just a Bernoulli map with 2 symbols. And in this case, we can compute again this characteristic function, and is given by this formula here. And this is the characteristic function of a polyhedral. With I will show you at the beginning what is the form of this variable, but I mean we know what it is. This one. Okay, to finish, just a few words on the assumption on the map in the quenched setting for this second technique. They are exactly the assumption which Gary presented you 2 days ago. Okay, so we have the derivative which is bounded. Then we have the number of, okay, dt is the number of branches, which verify this assumption here, uniformly bounded on the choice of omega. Then if we look at the monotonicity partition, okay, what is this? Yes. Okay, this sorry, I copied and glued. This is nothing to do with the assumption. I forgot to remove it. Then we have the functional space. In this case, is given by bounded variation, but with the choice of a conformal measure from the very beginning. So it's defined in this way. We have some covering condition. In this case, I put a uniform covering condition in order to simplify the presentation, but we have also more flexible covering condition. Contracted potential, as Gary explained 2 days ago, which are defined in this way. And also covering condition for the open system. Okay, these are technical conditions. Of course, they are difficult to verify in a concrete example. But for the example which I presented you before, these are easily verified for a simple reason. We took maps with linear slope, and mu omega was Lebesgue. It was just done in this way. But in our paper, we have other examples, a little bit more complicated than this. And all these assumptions must be checked. And okay, and at the end, okay, so we can apply this theory. So I stop here. Thank you very much.
Very much. Questions?
Yes.
Can I Sorry, in the setting of extreme value theorem, what is the logic of taking the all that is random? I mean, because all that is random, because the all is just the, if you are in the all, it means that you are just looking at some event, right?
Yes.
So you're looking at random event. It seems a little bit strange, right? Maybe.
No, but the question was the first time someone asked me this question was just a physicist. He asked me, suppose we are looking to some rare events, which is your orbit enters some small region. What happens if we are not able to localize precisely this region, but it moves? So in this case, we put randomness also on the on the choice of this all, where the position.
Yeah, that I understand, that you have randomness in the choice of the all, but I cannot imagine exactly what situation, like for example, that I'm worried about, I don't know, that there is some, I don't know, too high temperature or maybe a flood or something like that, right? That is a kind of a deterministic event, right? I don't understand. I cannot imagine what kind of random event.
You can have some uncertainty on the of measure apparatus in order to know exactly if your orbit jumps into the. But this is was a physical question.
I see.
And we also wrote another paper using an annealed approach, and where we move the all, and then we integrate also on the noise in order to get an annealed approach.
Okay, so I have to understand it as a problem of measurement.
Yeah, yes. But this is what I ask a question addressed explicitly by some physicists. So, but even mathematics, it makes sense. But
no, mathematics is okay, but I wanted to understand the physical motivations.
Okay, more questions? Okay, not, thank you. Thanks again. So, our next and final speaker is Giovanni Forni, and he will talk about effective equidistribution of nilflows and bounds on Weyl sums.
So first I'd like to thank the organizer for the invitation. I'm always very happy to be back in Pisa. I like it very much. And also I think it's my kind of privilege and duty to thank the organizer for everybody. So we should give organizer a big applause for the perfect organization. And okay, so maybe I'll begin with the talk. So the talk is going to be mostly kind of motivated by number theory. So it's a very different flavor from what we heard in many of the talks during this week. Let me just try to give you a kind of a synopsis of the talk. So on the blackboard before I really start. So this is about Weyl sums. So what are Weyl sums? So we take a polynomial of some degree k with some coefficient, some vector of coefficient. This would be something like ak x to the k plus, etc. a1x. Well, a0 doesn't really matter much, but let's put it this here. And then we look at exponential sums. Well, it should be a variable x here. Exponential sums of the polynomial over the integers. So we look at say expression like this. So this is going to be like sum from 0 to n minus 1, and here there is exponential 2 pi I p k a n. And then the question is to prove bounds on this. So question is essentially what we would like to say is that the wk an in magnitude is going to be big O of maybe n, and then here some power that will some gain of power exponent wk, and of course this cannot be true, right? Like this. So first of all, we want ak irrational, but also we want ak under some Diophantine condition. So ak satisfies some Diophantine condition. Let me not be specific here. Maybe Rod condition. So essentially, it's irrational. It's not well approximable by rational numbers. And then we can hope to have some gain here, wk. Now, so that's the problem from number theory. Motivation from number theory has several. One is, for instance, related to the zero-free region of the Riemann zeta function. This is probably the most kind of hyped, but there are other applications. These applications are tricky in general. So, for instance, this constant depends on k, and you need to know something about this constant. So there are also technical details. But why I'm interested in this? Well, one of the reasons is that for k equal to 2, then you can put here the word renormalization. And then for k larger than 2, so it's not clear what to do. And so I'm going to talk about what we do here. We get a result which is comparable to results that have been proved in the last, say, 10 years from completely different methods. You'll see that. But that's essentially my original motivation was really to look at how can we generalize or sort of push renormalization to situations which are similarly beyond it. And another situation where we have this situation, renormalization for some cases, and then when you go to similar cases, we are in trouble, would be like billiards. So this is just not part of the talk. So the subject of the talk stops here. But here I could put billiards in rational polygons. So rational, it means that the angles are multiples, rational multiples of 2 pi. And here, so this is renormalization. So it's okay, they can be studied by some renormalization techniques. And here, more general billiards in polygons. And here, I'm not saying that I have anything to say about this, but it's a similar problem that we know how to study certain situations by normalization, and then similar situations are going to be non-renormalizable, and it's not clear what one can do. So, okay, so this is more or less a kind of a sketch of motivations. Let me also add that renormalization is going to be hyperbolic, and the system I studied are going to be parabolic. And typically the relations is that the parabolic system is going to be the unstable, going along the unstable foliation of the hyperbolic system. So, but you'll see that in this class of cases that are related to nilflows. So, okay, so more or less, the first thing we want to do is to understand these Weyl sums from point of view of ergodic theory. So to do this, we follow Furstenberg. Furstenberg realized in the 60s, I guess, that one can prove the equidistribution of a fractional paths of polynomials by looking at skew shifts over the two-dimensional torus. So the skew shift is a map T, and we have the polynomial pKax, and for all k which are irrational, the sequence of fractional part is equidistributed modulo 1, and this can be deduced from the ergodicity, in fact, the unique ergodicity of the map T. So that's the result of Furstenberg. And the reason is that if we look at the iterates of the map T, then the ith coordinate is given by some polynomial of degree I. So in particular, you see P1, you see the rotation, which is the first coordinate. In P2, you see quadratic polynomial. In P3, you see cubic polynomials, and so on. And so if you look at the last coordinate, you get polynomials of degree k with a leading coefficient that depends on the frequency on the circle, and the other coefficients are arbitrary. You can just arrange the initial point, and you can recover all polynomials. So, in fact, in particular, it's important to know that the system is uniquely ergodic, so you can control averages of all points and not just almost all points. So, well, of course, if you have questions, or well, you can always please do stop me. So, okay, so now the question is, can we actually give an estimate to this equidistribution? So clearly, these exponentials are zero average functions. So we expect this. Well, we by the previous result, we know that if we divide by n, we get zero limit, and we want to get some bound. So in literature, usually what people look at is a max over the subleading coefficients, and the AK coefficient is, well, I mean, there are many results of this flavor, but one can assume that the AK coefficient is some Diophantine number. And the Weyl exponent is the optimal loss WK that one have under say some Diophantine condition on AK. So that's a usual way to state the result in number theory. But just to simplify a little bit, we want to know what is the largest W that we can put, say if AK satisfies a Roth condition, which is some kind of Diophantine condition. So yeah, here I gave a little bit more detail. So if we have in fact a Diophantine condition of exponent nu, then we may try to actually go with nu to some linear function in K and get some bound of the kind that I just outlined. Now, this problem has a long history, and you'll see how slowly this thing has progressed. So for the first bound was by R.D. Littlewood in case K equal to 2. And in the case K equal to 2, they in fact get 1/2 plus epsilon. You can be more precise, you can give logarithmic terms and so on and so forth, but let's forget about all this. So for Roth, say for Roth type, you'll have a half gain. And Weyl generalized this to all degrees, but you see that the WK is exponentially small. So 1 over WK is less than 2 to the K minus 1, which means that you can take WK to be 1 over 2 to the K minus 1. So it goes to 0 exponentially with K, obviously. Now, yeah, so maybe I should remark that what one could expect if you look at this sum and you look at, say, L2 norm, L2 mean with respect to coefficients, these exponentials are orthogonal. So from L2 point of view, you see square root. So in some sense, the idea is that square root should be the right bound, and there are in fact conjectures. I mean, I think number theory literature, there are conjectures that say that 1/2 should be the correct loss or gain, rather, for Roth numbers in all degrees, but we're very far from anything like that. So the big breakthrough on this was Vinogradov, and everything up to the result I'm presenting, which is I didn't say, but in collaboration with Livio Faminio, everything is based on Vinogradov method. So Vinogradov, basically the idea that I'm not going to explain in detail, the idea was to average over the coefficients and first study the average, the integral. So Vinogradov integrals is essentially an average of the norm of these Weyl sums over coefficients. And then from there, one can go back to specific coefficients. So Vinogradov was able to go from exponential to K square log K with some constant. And then there was a long progress to improve the constant, then they get rid of log K. And then Woolley went very close to proving Vinogradov's conjecture, and which implied that 2 twice K minus 1, K minus 2. In fact, he proved it in K equal to 3. And then finally, Bourgain, Demeter, and Guth were able to completely prove Vinogradov's conjecture, whatever that is, I'm not telling you. That implies the exponent KK minus 1, which is now the best known. Woolley then could refine his method to actually match this result. So all this is based on Vinogradov integral, so it's on averages, and the techniques are either number theory or a Fourier analysis technique called decoupling that has been developed by Bourgain, Demeter, and Guth. So the lower order coefficient in what there are results also on the lower order coefficients, but if you approach the problem from point of view of nilflows, it's very natural to just look at the top coefficient. So I'm just giving you results where the top coefficient is Diophant and the lower order coefficients are absolutely irrelevant. Although, of course, you want all of them, and this is a technique. I mean, this is in some sense the hard part, that to get all of them. Yes. And now the one thing that makes the game a little bit interesting, that Vinogradov integral now the estimates are optimal. So you cannot improve from that side, but the method of Vinogradov loses a lot going from the integral to the pointwise result. So of course we since we have another method, we can hope that we can do something, but I think this is not very likely, but still. Now, one can ask what is known about optimal estimates. Are these estimates optimal? The answer is, I sort of sketched that in some sense one hopes for a half. Now in k equal to 2, estimates are optimal. Indeed, we know that a half square root is the right behavior, but in higher degrees there is no idea. It's just is up for grabs what is the best behavior, although there are conjectures that say a half should also still be the behavior. So now why is this? Well, my answer to why is well known, since basically admittable that the quadratic polynomial sequences have self-similarity properties. I will give you a version of an explanation why that's the case. So then, once you have self-similarity properties, wow, you have an enormous literature. And, I just put some names through the years that studied the quadratic case, limit distribution, curlicues, a lot of stuff. Now, for higher degree polynomial sequences, it's not clear. There is no renormalization. The way we go about it is that we take the skew shift and we suspend it. So we take suspensions with constant roof. So it's like roof is 1. And it turns out that these suspensions are flows on certain kind of mean manifolds that will reappear a little later. They are filiform mean manifolds. And in the quadratic case, where we have self-similarity, we get the Heisenberg group. And then we have a renormalization scheme that is not hard to explain. I mean, it's more kind of a geometric. That is I call Heisenberg renormalization, and we explained it in 2006 paper. So you see that since 2006 we were trying to go to higher degree. So it took us 17 years or something like this. So, but anyway, so I'm especially happy to be able to present this because it was a long time coming. So no renormalization for I-step filiform nilflows seems to be possible. So what are filiform nilflows? I mean, again, let me repeat. We take the skew shift of the high-dimensional torus. We put a roof function equal to 1, and we do the usual suspension construction, which means that we go up vertical when we hit the roof at time 1. We go back to the base, the toral base, and we go at the point given by the action of the skew shift. And what we get is a nil manifold. So it's which has a Lie algebra, which has the structure that is presented here. So we call it a filiform. It's a special case of a filiform. So all the commutators are 0 except the one that I listed. Well, yk is the center, and the filiform mean manifold is the simply connected Lie group that has this Lie algebra, and then quotients over a lattice are compact nil manifolds. All finite volume nil manifolds are compact, and then there is a general notion of homogeneous flow. So in this case, it will be a nil flow. You take an element of a Lie algebra, you do the exponential map. We multiply to get the flow. We multiply on the right, and the lattice has to act on the other side. We do it with the left. I mean, these are conventions, and I can never convince Livio that this is why is this. Well, anyway, so this is the way we do it. So now, in the case k equal to 2, well, let me go back. So you see that in the case k equal to 2, you only get x, y1 equal y2, and y2 is the center because x, y2 is going to be 0. So you really get the usual commutators of the Heisenberg structure, and then we can begin on Heisenberg structure with self-similar nilflows. So what is a self-similar nilflow? Well, it's just a flow that goes on the unstable direction, an unstable foliation rather, of a partial hyperbolic automorphism of the Heisenberg Nil manifold. So Heisenberg Nil manifolds have like a little bit like two-dimensional tori, have automorphism. These automorphisms can be partially hyperbolic. They cannot be hyperbolic because the center is always neutral. And well, there are some special nilflows that go along the unstable. And these are what I would call self-similar because they are renormalized by a map. And well, these are a little bit special. So so we want to generalize this construction in some sense. And the construction is generalized in the following way. So we look at the group of automorphisms which preserve the center. And inside that, we look at the subgroup of those that also preserve the lattice. You can think of doing this with a torus, right? So if you do it with a torus, you don't have preservation of the center. You look at the automorphism. You look at essentially SL2R acting on the torus. And then you look at SL2Z preserving, say, the Z2 lattice. And you get some kind of a renormalization in this way. So in particular, the element of out gamma are those that that preserving the lattice give automorphism of the Heisenberg Nil manifold. So now the problem, of course, is that self-similar. So this is a general situation in the relation between hyperbolic and parabolic. Self-similarity is rare because we have to be in a special situation where we have an hyperbolic automorphism. If you think of the case of the torus, it's like saying that very few flows are actually have a slope which is an algebraic irrational of degree 2 or something like this. But there are many more linear flows. So what do we do for the many more linear flows? We define some kind of a renormalization scheme. In the Heisenberg case, this is what we introduced in 2006. So we look at the collection of all Heisenberg frames. Maybe I should use the pointer. I don't know how to do it. No. Well, anyway. Oh yeah. So you look at the collection of all frames, and with they should be Heisenberg frames. So the commutator has to be the center. This is identified with the automorphisms that preserve the center in some obvious way. Essentially, you can just fix one of them, and then you obtain all the other by automorphisms that fix the center. And D means the formation space, is some terminology. And then you look at the quotient over the automorphisms that preserve the lattice. This is the moduli space. So this is the moduli space of all Heisenberg structures on the Heisenberg manifold. The manifold here is fixed. Say H3R over H3Z is we are not going to change. And then we scale the Heisenberg structure. This scaling is by automorphism, so it preserves D. And then this is just a scaling, and we project this scaling on the moduli space. So this is defined. This definition, you can take it on the formation space D, but then you want to project down. And it turns out that what you get is some annals of flow on this quotient. So M is a quotient of the affine group over some natural lattice. So it's a 5-dimensional non-compact but finite volume manifold. And the renormalization flow is an annals of flow, but this is not really very important in some sense that is an annals of flow. So the partial hyperbolic automorphisms of the Heisenberg manifold are in one-to-one correspondence with periodic orbits. And we want to say that the approximate self-similar nilflows are the elements where X, well, are the X's, so are the flow generated by X for orbits which are forward recurrent. So we don't have a periodic orbit anymore, but we have some recurrence. So that would be some kind of approximate self-similarity. Notice that in the language of cocycles, so what is really going on here? In the language of cocycle, this means the following. It means that first we deform, and then as we get out of the fundamental domain in the deformation space, we apply an automorphism. So in fact, what we are doing by this formalism is to look at a sequence of automorphisms that is encoded by the trajectory of the scaling in the deformation space. So really you can think of this as replacing a single partial hyperbolic map with a sequence of partial hyperbolic maps, which is not just arbitrary, but it's just encoded by some dynamics on a moduli space. So then what is the relation between effective polynomial ergodicity of a nilflow and effective exponential mixing? Well, for the pH automorphism, essentially these are the same, more or less, right? So in the case of in the self-similar case, you just look at, you just obtain ergodicity, effective ergodicity of the nilflow by effective exponential mixing of the partial hyperbolic automorphism. Now, this exponential mixing, well, is more or less already contained in this paper in 2006, but then was also done by Frédéric Faure. All this is more or less very similar, very close, based on theory representations. But then Faure and Tsuji also can go to nonlinear, but just to mention it, that you can in the hyperbolic theory, actually in the partial hyperbolic theory of these maps, you can go nonlinear, and there is an important result by Faure and Tsuji in 2015. For us, everything stays algebraic and homogeneous. So in the generic case, well, what you get is Oseledets theorem. You want it with a spectral gap, and it will be an infinite dimensional cocycle. So in the self-similar case, the partial hyperbolic automorphism will have a transfer operator that acts on some space of distributions. Well, in the generic case, you have some cocycle, and necessarily you will have a transfer cocycle, with very similar to the cocycles mentioned by Cecilia Gonzalez Tokman in an earlier talk. This renormalization cocycle is just a transfer cocycle which acts on some Banach-Hilbert bundle over GT, which is the renormalization flow on this moduli space. Now, luckily, we are in an algebraic situation, so we don't do fancy theory of anisotropic Banach spaces. I wouldn't be able to do it right now, but so this is more or less the idea of a transfer cocycle. So basically, for any element of the deformation space, you put some space of distributions. This would be what you want to do, and then you have a trivial cocycle at the level of the deformation space. You don't touch your vector. This is the level of D, and of course, when you quotient, you will see appearing the action of the automorphism on the space of distributions. And now in our paper in 2006, we can get away by just taking as a fiber of this bundle the space of distribution which are invariant for the X vector field. The X vector, I mean, it depends whether you go in the future or past. So let's say that we go into the future, whatever it is, and then it's enough to control ergodic averages to look at the distribution which are invariant under X. If you want to do something more refined, then you have to look at the kernel of the square, the kernel of the cube, the kernel of the fourth power, and so on and so forth. And if you do that, you get a full Oseledets spectrum, and they look like that. Now, it's somewhat well known in this business that if you just look at ergodic averages, you have to stop at the first band. So you only see the -1/2. And but this is somewhat related to Weyl resonances. I mean, in the periodic case, so in the case of automorphism, this will really be Weyl resonances. And in the transfer cocycle, in the cocycle case, this is still kind of Weyl resonances. And the framework is really the framework that Cecilia mentioned. Although, of course, here we have a problem of a different flavor, but it's very similar. So all this can be done by the theory of unitary representation of nilpotent Lie groups, and we don't need fancy analysis, but we are in an algebraic situation. And now, so now what to do? So when we go to k higher than 2, we lose this structure. So there is no way of renormalizing in a way that, so what is renormalization? Okay, you can say you scale and then change variable. But when you change variable, you want to come back to the original manifold. So you want to see some deformation of the original manifold. This is possible only if the commutators don't blow up, because you have some Heisenberg structure, and then you scale it, and then you change coordinate by diffeomorphism, and you can come back near the original structure only if the commutators are not blowing up when you scale. Now, in other terms, to stay in this setup, you need to scale by automorphism. But there is no way to do that. I mean, we definitely tried. This filiform algebra doesn't have an automorphism that say preserve the volume. You can dilate it, but if you dilate it, you don't see anything. So what is the idea? The idea is basically the following. So, okay, so what is the renormalization actually doing, even a periodic orbit case? Well, the renormalization is telling us as we scale, as we deform, the geometry of the metric associated to the scaling is under control. In the periodic case, the geometry remains bounded. And in the recurring case, the geometry, is kind of bounded most of the times. And what do I mean by geometry? Well, the frame xy1, yd plus 1 defines some Riemannian metric where the vectors, you take them to be orthonormal. And so you have a Riemannian metric, you're scaling the metric by scaling the vectors. And this Riemannian metric will have, say, an injectivity radius, for instance, or other geometric features. And you want these features to diverge slowly. So this is a kind of heuristic principle. So the flow of X will be ergodic, quantitatively ergodic. This should be in some relation with the fact that in the space of metrics, as measured by some feature of the metric, which is relevant to the problem, the Riemannian metric diverges slowly. Now, yeah, here I just put some examples that more or less repeat the concept. So in the self-similar case, you could have an hyperbolic total automorphism or a pseudo-Nosov map. You could have a geodesic flow in constant negative curvature. You could have a partial hyperbolic Heisenberg automorphism. All these are the renormalization systems. They renormalize their invariant foliation. It's important to look at the full invariant foliation, unstable foliation, and not just part of it. In these cases, there is no divergence of the geometry because when you scale, the map tells you that actually you're back. So in some sense, what you see is a periodic orbit. So it's a compact set in the moduli space. So here, no divergence. And in this case, polynomial ergodicity is the same as exponential mixing, roughly. It's the same after work of many people, including Liverani, Giulietti, etc. So it's not an obvious thing, but the idea, I guess, comes from Margulis. But then the problem, of course, is that you want to control all points and so on. So there are questions? Yes. Sure. Good question. So the rows, you see, I want the rows to sum to 1 because I want the deformation to be to preserve the volume. Otherwise, my manifold is just dilated. But the row at this point are kind of arbitrary. Yeah, I can just anticipate, and the point is that the row will be chosen to optimize the final result. So the row are not, I cannot dream of the row 1, row D. I wouldn't know. It's the analysis that tells me what row are optimizing my final result and will give me the result, which is this exponent. So of course, a priori, I could take the row should be positive and should sum to 1. But yeah. If you change the row, you will get different exponent in the end. So you get suboptimal estimates. So there is an optimal choice of rows, that will give you the best possible, the best result you can attain. So, okay, so that's more or less a comment on this. And yeah, and then yeah, there are some classes where you have flows. We have parabolic systems which are almost self-similar, so it's still renormalizable. So in particular, for instance, you can have the renormalization could be the modular flow, so the geodesic flow on the modular surface, and you have the general linear flows on torus. So this is more or less a relation. You can have the tacular flow or the Rosevich induction, and you have a generic translation flow. And I just explained you can have the Heisenberg renormalization flow, and the flow will be a generic Heisenberg flow. So this is, unfortunately, this is all. I mean, well, there are the self-similar, they're renormalizable, and that's all I know. So in a sense that I don't know more examples. Well, there are so-called orospherical unipotents in quotient of semi-simple Lie groups, which of course belong also to the self-similar category that I didn't mention. But so inspiration for this scaling approach in part come from translation flows, but this is, you know, if you know what is measures unique algorithmic criterion, you understand this. Basically, the idea already there is that you have this renormalization flow, which in that case is tacular flow, and you get ergodicity if the orbit of the renormalization doesn't go to infinity too fast. So that's you know, a natural idea that is not I'm sure I'm not the first trying to pursue it, and the divergence of geometry should be controlled by some kind of Fountain condition, and but you know, more or less explicit means that usually it's not explicit. So it's well, you know, in this case on nilflows it's quite explicit, but for translation flows it is not explicit. So okay, so I want to make the case that there are some abundance of dynamical systems which are not renormalizable. All the non-orospherical unipotent flows in quotient of semi-simple Lie groups. This is an area often called effective Ratner theory, which is pursued by many people, and there are some recent results, very recent, by Lindenstraum, Ahmadi, Zhang, and Lei Yang in some special case. This is in this case here of non-orospherical unipotent flows. Then there are Eier-Step nilflows, which is the topic of the talk, and then there are billiards in general polygons beyond the rational case. So these are some classes of example that we see this dichotomy, renormalizable, non-renormalizable, and where the game becomes kind of difficult. So yeah, this orospherical, non-orospherical means that in the so-called non-orospherical case, there may be some hyperbolic map or flow, but the flow you are interested in is not the full unstable. So it's some one parameter subgroup, because we are in Lie group context, is given by some one parameter subgroup of the unstable, and unstable is high dimension. Okay, so all right, so now maybe I should look at the time. I forgot what time I began. But more than 10 minutes. It's not so much. Okay, so yeah, so let me just basically state the result. So this is at least I state the result. So the result is the following. So we look at filiform nilflows. So all flows that are, I mean, flows which are on a quotient of the quotients of the nilpotent group with this Lie algebra, the algebra here, that I already put on the slides. And again, I said that they are renormalizable in case k equal to 2, but not in case bigger than 3. And I think I actually can make concrete that it's really not possible to renormalize them in a sense that there is some recurrence. And the result is the following. So if we have a flow, nil flow on this nil manifold that projects to a linear, so there is always a projection that on the so-called abelianized. So if you forget all the commutators, then what you are left is if you kill to 0 all the elements which are commutators, you are left with two vector fields. So the Lie algebra will be R2, and so the quotient will be a 2 torus. So it's a well-known classical thing that a Nil manifold like this projects on a 2 torus. The Nil flow projects on a linear flow on the 2 torus. And these 2 torus basically decides whether you have ergodicity, a unique ergodicity, or no. And there is a frequency there, which is essentially corresponds to the top coefficient of the polynomial, as we've seen earlier. And we can get away with a Diophantine exponent that goes up to k over 2 or k over something like this. We need some amount of regularity, but then you see basically this is saying that we have a speed of ergodicity which goes like with this gain of 1 over k minus 1 plus epsilon. So here is because I divided by t, but if you just multiply by t, you see that this is exactly the wk of the Weyl sum. So corollary of this, well, the corollary, I basically announce it. So the corollary is that if you look at the Weyl sum, then you get under condition, Diophantine condition on AK up to k over 2 Diophantine exponent, you get a bound like this. Now this bound is the same as the one coming from Vinogradov main conjecture. Again, Bourgain, Demeter, and Guth. We have a little, they do better on the Diophantine exponent. They go up to k minus 1. So the result is slightly stronger, but we also have some other, I mean, there is some disadvantage here and some advantage in some other part. And it looks like we have a much better dependence on the constant on k, which is very important for applications. So, but this is, we haven't explored yet. So I'm not sure. And there is a nice survey article by Bourgain that I quote here, where he explains shortly and clearly the relation between Vinogradov conjecture and Weyl sums, and states the result. Now, proof outline, and here is like hard to, because with not many. Well, so the point is that we start by looking at what is called the cohomological equation. Why do we look at the cohomological equation? That the main reason is that we are interested in ergodic integrals, and everybody doing dynamics knows that if you do the ergodic integral of a coboundary, you get something bounded, especially if the transfer function is bounded, right? So in some sense, the heuristic here is that if you want to know deviation of ergodic integrals, so the growth of ergodic integrals, first you have to get rid of coboundaries because they don't contribute. And the obstruction to be coboundary, which are the invariant distribution, are likely to be responsible for the deviations. And of course, this is a little bit, it's true, it works, especially because we are looking at everything is smooth, everything is nice. So in some sense, you can say that Weyl resonances are given by invariant distributions. In the language of hyperbolic dynamics, that's what we heard in the conference. This is more or less what I'm trying to say, is that in this case, if you look at a similar situation, then you do exponential mixing, and then you do Weyl polycot expansion, and you only look at the first term, because the other terms you cannot, for ergodic averages, they don't matter. And then it turns out that in fact the Weyl states are given by invariant distribution morally. So okay, I try to explain that the ergodic averages of coboundaries are bounded, and so that's in some sense the heuristics here. Questions? So how do we do that? Theory of unitary representations for nilpotent groups. So very, very, very simple. In fact, the theory is well known, is easy, and so then introduce the appropriate scaling. This is Paolo's question. What is the appropriate scaling on the Lie structure? Well, anyway, there is an appropriate scaling that it will, in fact, determine only a posteriori. And then there is a very frequent issue that arises naturally. Why? Because we want the transfer function u, right? There is a transfer function u. We want it to be bounded. So we want C0 bounds or L infinity bounds. But the theory of unitary representation is a L2 theory. So we have L2 estimates, and we want to go from L2 estimates to C0 estimate. So here there is some kind of Sobolev trace theorem, and we have to do it for scaling metrics. And the constant in the Sobolev trace theorem depends on the geometry. And here where this geometry is coming in. So we need to know that for the scale metric, we control the geometry enough to be able to bound the constant in the Sobolev trace theorem. Now, you may think all this is technical, but it is not, at least is a way of looking at the problem, of course, but this thing really shows up in, especially, for instance, in the logarithmic corrections that appear in degree 2, for instance. In degree 2, you have logarithmic corrections that are exactly explained by the generation of the geometry. So it's really relevant. And then, well, there is a notion of average width, which is really whatever it is that we use to control the geometry. And the hardest part of the proof is to control, where we were stuck for many years, is how we prove bounds on the average width of orbits. So how do we control the geometry? So the scaling part is easy in some sense, but the control of the geometry is very hard because we don't have moduli space, we don't have recurrence, etc. So 1 and 2 are based on representation theory. And now how much time do I have? 2. More than 5 minutes. So time has slowed, or maybe I'm going faster and faster. So anyway, okay, so this is plenty of time. I think that I may slow down. So any questions? Yes. Yes. What? You mean higher order terms? Well, I mean, there are no higher order terms in this, yeah. No, we don't project in a linear flow. No, we don't control. We don't have an asymptotics. So you just have a bound. Yeah. No, we are not projecting on the linear flow. This flow is on the manifold, right? We are not. There is no projection. I mean, at this point, there is no projection. So this is really a statement about a manifold on this. I mean, about a nil flow on this nil manifold of some dimension. There is a base torus, but the statement is really about the nil flow, and the return map of this flow to some transverse torus is the skew shift. So that's the way we go from the theorem to the corollary, right? And the fact that the root function is constant makes the translation easy, automatic. Otherwise, of course, we'll be in trouble. So, okay, right. So this is the optimal scaling. So you ask, what is the optimal scaling? This is the optimal scaling. And so it's just a scaling, right? So we just take the Lie algebra and scale it. And then we look at the Sobolev norm of the invariant distribution. That we do this, of course, we first have to find the invariant distribution in Fourier representation. And then we look at the Sobolev norm of the invariant distribution with respect to the Sobolev, with respect to the scale metric. I mean, a metric comes with a natural Sobolev norm because we have unit size vector fields, and we can compute this one here is the scaled Sobolev norm of the distribution, and it scales exactly like this. If the scaling is this, and indeed this is the optimal. We cannot do better. So why this scaling is because we cannot do better on this exponent, and well, we exactly get the same exponent as these other people from completely different methods. This is just saying that this is a scaling result, really. Maybe one can go beyond that. So scaling results, in some sense, are first level of cancellation that you can get. So I try here, but maybe this is too ambitious in a talk to give you a flavor of right, scaling factor explained. So how does it work? Well, you work with the theory of unitary representation, and you know that the x vector field is the derivative, and the other vector field represent as multiplication operator. I mean, I'll simplify. They may be non-homogeneous polynomials, but this is the main situation. You know, if you know quantum mechanics, you recognize the Heisenberg representation, ddx and I lambda x, right, in k equal to 2. And then the scaling, basically, the scaling you want to use is the one that actually comes from a scaling of the variable. So you impose the condition that the scaling is a scaling of the variable, of the representation variable, and moreover, that the exponent you get add up to 1. So you scale, in other terms, the recipe scale the representation variable by some amount, which of course doesn't depend on J, on the variable. I mean, it doesn't depend on the vector field, and do it in a way that the sum of all the scaling exponents of all the rho J that you get add up to 1. And then what is the invariant distribution is just the average. And then you know, it becomes like a simple exercise to, I mean, really simple to compute the Sobolev norm of this average with respect to the scaled vector fields. So it's not, well, I do it here, but I don't have the time. So you see that it's just a simple calculation, and basically you are in one variable L2 space, right? L2 of R, and anybody can do this. And now, well, this is the part on the geometry. Probably I will skip it. The idea on just I give you just one sentence. The basic idea of the bounding the geometry is to go to a suitable cover. So, and the suitable cover is defined is an algebraic construction based on this diagram. I guess I will just skip it, and if you are interested in more explanation about what this diagram means, maybe we can discuss it after the talk. So it's essentially an algebraic construction that constructs a cover where the problem can be transported, and this cover has better properties, and we can actually control the geometry on the cover. We never control the geometry on the scale of the scale metric on the filiform and manifold. In fact, there we don't know how to do it. But in some sense, there are these closed returns that get untangled when we go to the cover, and we have better property there, and etc. Thanks for your attention.
Very much. Questions? So I have an extremely vague question. So can one say in a few words what one would need to understand to apply these ideas to billiards in non-rational polygons?
Well, I mean, yeah, that's a good question. So one can apply these ideas provided one can control the geometry. So the hard part is really always how to control the geometry. So the scaling is quite clear. What is
the last step in your
exactly? So that's the hard part. Yes, the rest is basically done. But the control of the geometry is very difficult, and so far I haven't been able to pull it out. But it looks plausible, and maybe someone will be able to finish it. But yeah, that's the situation. So the control geometry, you have to do it in some sense ad hoc based on some specific property of the problem. So in this case, we have an algebraic structure, and we figured out eventually that the best idea is to go to some cover. And but in the case of the non-rational billiards in non-rational polygons, is a bit more unclear how to do that. So that's the answer.
More questions? Okay, if not, we thank Giovanni.